All right, welcome everybody to the Miriam Radio Club's lesson. This is our advanced topics class, but this week I'm not really going to get super advanced. It'll probably be a little more advanced than Dan was last week, but I had some things that I liked about his presentation last week, and then I had some things that I thought might help people understand some of these topics a little bit better. So, I took an old talk of mine and I tweaked it and polished it a little bit and made a few changes to it. And I think you guys will like this one. So this is general electricity and electronics. Keep in mind, last week Dan talked about electricity and electronics. I'm not trying to replace the talk that he did. He did a great talk. This is some additional information that may be useful. And we're probably going to burn through the first half of this really quick because we should all be familiar with these topics at this stage. But let's get started. So, what is electricity? Electricity is the movement of electrons. Can you see that, Justin? You're squinting. It's not great. There's a lot of text on some of these early slides. These are things that I wrote several years ago, and so I wasn't quite as good in slide production as I am now. And I'm not saying I'm great now, but um, if you think about it, atoms have a couple of parts to them. They have the nucleus, which is the center part that has protons and neutrons in it. And then they have what we think of as a cloud of electrons flying around this thing. And the electrons are in different shells. If you reach way back to your high school chemistry class, you'll remember the P shell and the S shell and things like that. And you'll think, man, I thought I never would have to hear that again after high school chemistry class. And you won't hear it again. So, moving on. So, there are some important concepts with electricity. There's AC versus DC. Dan talked about that last week. Charge, which is the presence of a either positive or negative charge. It's caused by either an accumulation of or depletion of electrons on something, right? So, a positive charge on something is because there aren't enough electrons. A negative charge on something is because there are too many electrons. Voltage, we talked about, that's like the pressure of the electricity. Current, we talked about that. That's like how much electricity is moving. Resistance, we talked about that. That's like how hard it is for electricity to move through something. Uh, Capacitance, we talked briefly about that. That's like being able to suck up some energy and release it afterwards. Inductance, we talked briefly about inductance, but
Well, yeah, we did.
we did in the concept of transformers, right? And then power, which is the ability to do work. So let's dive into this and talk about some of this. I'm going to use a thing called the water analogy, which can make a lot of this stuff easier to understand. We're all familiar with water. We know what it is. We know how it behaves. You can think of electricity as similar to water. It behaves very similarly, not entirely exactly the same. And we'll talk about differences as we go through. But if you look at the behavior of water in a particular thing happening, and then you look at how electricity behaves in something, you can draw comparisons between those two. Okay. So the water itself is the charge or the amount of electricity, electric potential that you've got, right? The voltage is like the pressure of the water. If you turn your tap on at home and you open it a little bit, some water comes out. If you open it all the way, lots of water comes out. That's the pressure of the water, right? The current is how the flow of the water. So if I have a bucket and I stick it under my faucet, current is basically telling me how fast my bucket is going to get full. If I have low current, my bucket will take a while to get full. If I have high current, my bucket will fill up very quickly. Okay. Yes.
Go back to the voltage
Okay.
definition, because,
The pressure of the water.
yes, but
The,
you explained it as current.
did I?
Yeah,
Maybe I did. Okay. So the voltage is the pressure. It's like how hard the water is pushing.
yeah, so to use the analogy, you turn your faucet on, and if you put your finger at there, you
You
can
feel the
you can
pressure.
feel the
That
pressure.
was an analogy that you used.
So you see in the water going down, that's actually current.
Okay. Yes, you're right.
So
You're right. So technically, the voltage and the current is how fast the bucket fills up, right? It's not, if I have a lot of pressure, but very little current, my water is going to come spraying out in a tight little stream, but it's still not going to fill the bucket up fast, right? If, on the other hand, I have a big open tap and I only have a little bit of water pouring out of it, well, that's also going to affect it, right? Resistance is equivalent to the size of the pipe that the water is flowing through, okay? So think about that as how hard it is for the water to get through the pipe. If the pipe is constricted, it's harder to get water through. If the pipe is open, it's easy. Same thing with the electricity. If the resistance is high, it's hard to push the electrons through. If the resistance is low, it's easy to push them through. Okay?
I think the faucet thing's a good analogy for the resistance, right? Because when the faucet's on,
Yeah,
it's
as
high resistance when it's open.
I can close my faucet down and make more resistance to the pressure and control how much current actually is flowing through, right?
Or sand and.
Or I put sand. I don't have any.
That's what it says in there.
Where does it say sand?
It's just
Oh, sand in the hose?
Yeah.
Oh, where do I have that on here?
lower level.
Oh, okay, I see it. Yeah, okay. Think of that as like a blockage in the pipe, right? It's harder to push things through that blockage. Okay, so in our glossary of terms, we have voltage, which is the electrical pressure. The symbol is E. The voltage is measured in volts, which the symbol for volts is capital V. Dan went through all of this stuff too, so I'm going to do it really fast. Current is the flow of the electrons. The symbol is capital I, and it's measured in amperes or amps, and the letter for that is A. The unit is A. Resistance is the difficulty for electrons to move. The symbol is R for that, and it's measured in ohms, which uses the omega symbol because they had to be different. O was too easy to confuse with some other things like zero, so they chose not to use that O. Power is the ability to do work. The symbol is P, and it's measured in watts with capital W. One thing that I don't think Dan mentioned, all of these unit types, volts, amps, ohms, watts, farads, and henries, are named after somebody. That's why we capitalize them. And they're named after the specific people who figured this stuff out. Maybe 100 years ago, maybe 500 years ago.
The last screen of the presentation had all of the people.
The names, yes, yes. So you can think of electricity being like water flowing through a hose, right? AC versus DC, we talked about this last week. Direct current, the electrons move around the circuit from a negative to a positive potential. On alternating current, the electrons just move back and forth all the time. So the same electron is sitting in that wire. It never leaves that wire. It's just going to go back and forth a little bit each time. Why does it do that? Because that's how it works. It's able to do work by moving. Doesn't matter that it only moves a little bit and then moves back. It's still able to do work in that process. All right. So charge is like the amount of water you have. Think of the power stored in a battery like water in a tank, right? The more power you have, the more work you can do. When you run out of water, you can't do any more work. But you can pump water back into the system. So you can raise that water from the bottom back into the tank at the top. That's like recharging the battery. Okay. This is the water analogy, right? If you think about the voltage as equivalent to the pressure, think about if the water is in a tank up above your head, it's going to have more pressure than if it's in a tank sitting on the table. This is why in places where the land is really flat, they have big water towers. They pump the water up into the tower, and then the pressure of that height pushes the water throughout the entire water system in the town. We don't have a lot of those around here. They have some out by Hercules, but we don't really have a lot of those around here. We mostly have tanks that are at ground level. But you will see those if you travel to the Midwest. You will see a lot of those towers. Every town has one. Current, again, this is equivalent to the flow of water in the system. So you can see in my diagram here, I have either the same amount of pressure but a bigger or smaller pipe controls the amperage being higher or lower, or a different amount of pressure and the same size pipe or wire controlling the amount of pressure. So you can see the difference that both of those factors, the pressure, the voltage, and the current, the amperage, go together to make how much charge you have, right? Resistance is like the diameter of the pipe. So in a narrow pipe, it has higher resistance. It's harder to push the water through there. Same thing with the electrons. Ohm's law, Dan talked about this. I'm going to skip over it. I'm going to try to skip over it. The power law is the same, except with P, I, and E. Power being the ability to do work. Now, there's a question for you. In physics land, if I pick this mug up and I raise it up and I put it back down, have I done any work?
Your muscle have.
But have I done any work to the mug? No.
Yeah, but that's not zero.
The net work is zero, right? The net work done was zero. Now, I'm tireder from doing that because I used energy to make that happen, but no actual work was done. So power is the ability to do work, and work is defined as making something change. Okay. So I think that's an important thing to keep in mind.
So is that why my test tells me that I'm running around a lot but doing no work?
Yes. Yes, that's exactly why. That's exactly
I
why.
gotta work on it.
Yes.
It worked, right? The work you did was creating heat, which is something.
True, true, right? I mean, technically I did do that, right?
It's energy to heat,
But-
the cup
But
didn't-
has anything happened to the mug, right?
The
No.
mug did not.
The mug has not had any work.
It had potential energy. and
It
then
it
had
did.
to-
I did this is work. I did work here. But when I put it back in the same place, that work is undone. So, all right. We're also going to talk about basic electronics.
Yeah, it's a good refresher.
So these are the basics for electricity. We want to do some more complicated things. So when we start getting into this, we start talking about electronics. And I know, Dan, you're going to talk more about electronics next month, right? But we're just going to hit a few things at this stage. Electronics lets us do things with electricity and circuits where we use the movement of electrons to do things other than just push each other around and heat stuff up. Now, I'm not trying to make little of pushing electrons around and heating stuff up because that's how my toaster works. And I love toast. So if I didn't have the ability to heat stuff up by moving electrons, toasting my bread would be a lot harder. But we want to do things more complicated than that. Later, we'll take a step up from electronics and we'll talk about logic circuits. Let's talk about some basic symbols. These are symbols that you're going to see on the test, right? For the technician and other exams. And I don't know why I have this text over here: battery, wire, resistor, capacitor, inductor, transformer, diode, and transistor. I don't really have pictures for those, and I should have had pictures for those. I'm not sure where they went. And then logic components, we'll talk more about these towards the end of the presentation. I actually have some good information on these that I was not able to include before. But these are the symbols that you'll see on a schematic to indicate various types of device within the circuit. This is the schematic that is included in the technician exam, one of them. And you may have to answer a question on this. You may have to say what each symbol is. So you'll probably have like one question on this, and it will be either is number one, what is number one, what is number two, what is number three, what is number four. And these are the things that they are, right? This is this chassis ground. Then you've got the battery, you've got a lamp, you've got a transistor, and you've got a resistor. Again, this symbol is the ground, right? And then these are some kind of inputs.
So since this is an advanced class, let me just ask everybody. Why the chassis ground? Why do they not just show a regular ground symbol? What is important about the chassis in electronics?
You might,
This is just a synthetic example, right?
yeah, you might touch the chassis
Well, all of voltage is
potential between 2 points,
potential
right?
of some number. And so it uses a, it has to have a, starting point, and that chassis is where all of the electronics are grounded to, as you can see that. So that when I measure voltage, I'm measuring it in relation to the potential of the chassis. So it's acting as zero. Now, that chassis may not be 0 volts, it could be 3 volts. Okay, so anything that you measure will be in relation to that. So all I'm saying is the chassis is different from
Earth ground.
earth ground.
Yes.
Yeah.
And earth ground being the symbol that has the big line, this little smaller line, kind of like a triangle shape, upside down triangle. And that's indicating actually to the ground. Yes, Stan.
Oh, yeah. Transistor, that's an NPN transistor.
We're going to talk more about transistors in a minute.
Easy way to remember that.
Not pointed in, yes. There are PNP and NPN transistors, and the little arrow is either pointing in or it's not pointing in, right? So that's an easy way to know that. We'll talk more about transistors in a few minutes. This is a diagram that's in both the technician and the extra exam. They ask about different things, but this is the same diagram that's used in both the technician and extra. Extra, they're going to ask you about the SPST switch. SPST is single pole, single throw. And that's this guy over here, number 3. And basically what that's meaning is there's one pole, that's where the switch starts, and you can either throw it or you can not throw it. It can either be closed or open. And that's the only thing it can be. It can't be anything else. There's no like half open for a switch like this. You'll also see double pole, double throw switches, double pole, single throw, single pole, double throw. There's even triple throw and multiple terminal switches, but you won't see those on the exam. On the technician exam, you will be encountering the transformer, which we did talk about last time, and the capacitor, which is this guy. And you'll notice what's different between this one and the one on the earlier slide. On this slide, there's not that slide. On this slide, there's a capacitor here. Do you see what's different between that one and this one? One's polarized and one's not. So if it was 2 straight lines, it doesn't matter which way that capacitor goes into the circuit. Either direction is fine. It works the same either way. But this one, the side that's shown with the curve, needs to be on the ground side of the signal. Otherwise, it's not going to work the way you want it to. Yes. Then we've also got an LED on here, and that's this little thing that looks like a diode with little arrows coming off of it. That's indicating that it is an LED or light emitting diode. And then you've got a variable resistor. You see this resistor here has a little tap, a little arrow pointing into it that can be moved to different amounts. So it can be a different resistance depending on if it's at this end or this end. You can actually change that in real time. Usually you're going to see this indicated as a potentiometer or a knob on your device, like a volume knob. Although most of the devices nowadays have like, you'll feel little clicks when you turn the knob. It's actually some kind of counter that is telling the control circuitry, hey, the volume went up a notch, and doesn't really care what it was before or what it is now. It just says it either went up or down a notch. But on a real knob, a real potentiometer, it will have a place where it stops, where it's at the minimum amount of resistance, and a place where it stops, where it's at the maximum amount of resistance.
You'll see a lot of circuit boards with little teeny, cubes on there with a
little screw thing on top. Yeah.
Those are the same type of thing.
Yeah. Yeah. All right. And then this is the last one that you'll also see on the technician. And this diagram shows a few things. There's an antenna over here and a variable inductor, which is this guy. So you see the little inductor symbol, and it has the variable arrow thing, just like the uh, variable resistor had. There's some other things on here. You don't really need to know those for the test, but they are variable capacitors. And this is an AC power source over here. Why do we call it an AC? Why do we use an AC power source in this? This is a radio circuit. This is a radio circuit that is being tuned by this inductor to be resonant on this circuit. So this is essentially what's happening here is an antenna tuner. Yeah. Yes, they did. They had like a bar that a thing would move across the bar to, yeah, yeah. Oh, let's see. And then this is the last one that the general exam would have. And there are some things on here. There's a field effect transistor, which is this guy here. It's a little bit different shape from the other transistor that we saw. We'll talk more about transistor types in a minute. There's an NPN, not pointed in transistor over here. The Zener diode is this diode that has this little line on it like this. I'm not going to talk about the difference between a Zener diode and a non-Zener diode, but that's what the symbol is. A solid core transformer. Here's a little transformer, and it has these lines in the middle indicating that it's a solid core. If those lines weren't there, it would be a non-cored transformer. So two inductors together make the transformer.
If it's lines, then it's a net. If it's dotted, then it's ferrite. If it's nothing, then it's airborne.
Good to know. Thanks, Dan. And then the last one that you might be exposed to is the tapped inductor, which is, where is it? This one over here. And you can see it doesn't have an arrow on it. It's not variable. It's an inductor that we're snagging something out of the middle of it for some reason. Okay. Yeah, it's tapped. So it's like we have this full inductor here, but we're only using a portion of it for our circuit. All right. So let's go back to the water analogy and talk about how these things work in terms of water. Okay. So we talked about a resistor before. You've got your source of energy, your battery. You've got your wire. You've got the resistor. And then you've got more wire on this side. Think about that happening in a circuit. You've got energy coming out of the battery, going through the resistor, and typically producing heat, and then going back into the battery. So this would be how a resistor works in a circuit of water. So what about a variable resistor or a varistor? Think of it like a valve you can open and close, right? As we talked about earlier. When it's mostly open, the resistance is low. When it's mostly closed, the resistance is high. Okay. Let's talk about a diode. A diode is a one-way device. Electrons will only go through it in one direction. They won't go back the other way. So in water, we look at this and say, well, here's a pipe with a check valve in it. So as long as water is going in this direction, the valve will be open and the water will continue through just fine. If the water tries to come back the other way, the valve will close and it won't be able to get through. That's essentially how a diode works. Okay. So here's an actual conversation about the different types of diode, the Zener and Schottky. Zener diodes will allow electrons to go in the opposite direction if the voltage is above a certain level. And Schottky diodes have a very low current drop and operate very quickly. So that's why we would use those. A light emitting diode will glow with a particular color as current passes through it. So you'll see red diodes, green diodes, LEDs, and yellow typically. And I've seen some blue ones too, but I'm not sure how those work. It depends on the material that the diode is constructed from.
I mean, yeah, phosphorus will change the color, right?
Yeah. Yeah, so they can do that. Yeah, yeah. but the actual diode material will emit a certain wavelength of light, depending on the material. Capacitance, remember we talked about capacitance as being a way of storing the charge, okay? In the water environment, imagine we have a big tank with a rubber baffle in the middle of it. If I put more water in one side and increase the pressure in that side, it's like that rubber baffle gets pushed over towards the other side. And then when I let that come back out, the rubber baffle pushes back and pushes that water back out. That's essentially what a capacitor is doing with electrons. I can put them in on one side, and then it's like they're increasing the voltage inside there, the pressure. And then when I stop putting them in, they want to come flying back out again. So in an electronic circuit, we use a capacitor to moderate or smooth out a signal that is changing. Okay.
How many people have a tank right before their water heater?
Everybody who has a modern water heater should have one because the code requires that now. So if you don't have one of those and you ever replace your water heater, you will have one. If your plumber doing your water heater install is actually worth his salt. To change things again, right? Yeah. But yeah, so there's lots of different types of capacitor: electrolytic, ceramic, film, paper, silver mica, glass, and vacuum. Capacitors are typically defined by their dielectric, which is the material that separates the two sides. So um, depending on what type of capacitor you have, you'll see capacitors in on a circuit board, and they'll either be these like little brown discs. That's one particular type. That's which one is that? That's the ceramic.
Yes.
Yeah. And then the other type you'll see is like a cylinder, and those are the, yeah, so essentially it's like layers wrapped up in a circle. And then you'll also see ones that are like a blob of plastic, and those are the um, electrolytic ones, if I recall correctly.
I felt students that, one Faraday capacitor was pretty challenging to build.
Yes.
But they've gone now, these kids with these stereos in their cars.
Yeah.
They have huge capacitors.
Wow.
The ones I thought couldn't be built.
That's kind of dangerous, but okay. Well, all right. Inductance. Yeah, sure.
One type of capacitor that I think is interesting to hand radio people is your magnet antenna on your car. The metal doesn't touch the metal, but the reason you're able to use your car as a ground plane is because you just build a capacitor.
Yes, your antenna is a capacitor, right? It's essentially separating the two halves, the ground and the driven side, with a dielectric, which is the mount that
Right.
the antenna is sitting on.
Talking about inductance and capacitance and antenna to them.
Yeah. Yeah, it's a big deal for radio stuff.
Okay. So inductance, this is one that was confusing to me until I saw this water analogy. And the idea is if I've got current going through a coil of wire, inductance is the desire of the conductor to oppose a change in the amount of current flowing through it. So if I've got current running through the wire and it's just cruising along, it's fine and happy. But when I try to add more current or take some current away or change the direction of the current flow, it doesn't want that to happen. The coil wants that to keep going the same. So in the water analogy, think of it like a water wheel that you are pushing water through, and it's as you first start to do it, it's hard to push it through because you got to start that wheel moving. But once it's moving and up to speed, it wants to keep going. So if I suddenly stopped running water through it, it's going to take a while for it to slow back down and stop, right? This is how an inductor basically works. As I'm putting current in, it's going through and it's struggling to go through at first, and then it gets easier as it builds up that momentum. And then if I stop, it does the opposite. It takes it a while for that charge to go away. And this is how transformers actually work. We have two inductors that are making a magnetic field, And as I generate a magnetic field on one side, it induces a magnetic field in the coil of the wire on the other side. And depending on how many turns my coils are, that steps up or steps down the voltage. So it's kind of a cool idea when you think about it. It stores energy as an electric field, or not as an electric field, as a magnetic field. Capacitors store the energy as an electric field, but the inductors store it as a magnetic field. And they depend on this um, property of electricity moving through a wire is that it creates a magnetic field. So that magnetic field is built up and it takes time for it to decay as I adjust the current going through that coil. Yes.
Point out, the first one is air.
Yep. Like we were talking about before, the air core inductor, iron core, the ferrite core, and then this one is a variable core. And that's one where I can actually move the core inside the conductor and have some amount of core or not as much core, depending on what I want to do with it. All right. Transistors, I had a terrible picture for this, and I still have a terrible picture, but this picture is a little more accurate and easy to visualize. Think about a transistor as like a variable valve controlled by another signal. Okay. So it's not like a varistor where I set it to something and leave it there. It's able to be controlled by something else in the circuit. Okay. There's typically three lines that we talk about. And in this diagram, there's a couple of different names that we'll use in other types of transistors, but these are the two basic types that you're going to see. The NPN, remember, not pointed in, the arrow is pointing out, and then the PNP is pointing in, okay? They have the collector and the emitter and the base. And on this one, the collector is down here, the emitter is up here, and the base. So how do you know which is which is the collector and which is the emitter? The emitter is the one with the arrow on it. Okay. So it's showing where the electrons are going. This one, the electrons are going in and they're being collected out here if the base allows it. This one, the electrons are coming in from the collector side, and if the base allows it, then they're coming out. Okay. The base is the controller, and it's going to define if the electrons are allowed to go through and how many of them are allowed to go through at a particular time, depending on what the value of the base is. Okay. So in the water analogy, think of this is for the NPN. Think of the collector up here. The base is over here, and then the emitter is down here. So if I push water through here, it pushes this valve open, which causes this valve to open and allows more water to come through from up here. If I stop pushing water through from here, then this valve closes. It's on a spring. It closes, which forces this valve closed and stops water from going through here. Why would we want to do that? This is how an amplifier works. I can take a large signal coming from here, and with a very low signal here, I can modulate that pressure, that signal coming through. Same thing how it works in a transistor. Depending on what value I put on here controls how much comes out. If I've got an AC signal generated from my voice, for example, I can take my radio signal generated by some kind of oscillator and increase the power output of my whole thing here. I have very little power over here generated from my voice, but I might have 100 watts of power sitting here that only gets through when this signal lets it get through. So that's basically how transistors work. And this type of thing was originally developed in a tube form in which there was an emitter that was usually a filament that would heat up, and by heating up, it spewed out electrons. And then there was a grid that controlled how many electrons could get through by either sucking them off or not sucking them off. And if they didn't get sucked off, they went through and hit a collector on the other side. And that's how a tube works. What we call a triode tube. There are three parts of it. There's the energy going in from the filament. There's the uh, emitter or the base, the grid that draws off the electrons or allows them to pass through. And there's the collector that collects them on the way out and sends them through. And so that's how tubes were originally developed to do amplification. Yeah, the plate. Okay, so there are other types of transistors that you'll see in different places. The ones before that we talked about, the NPM and PNP, are called BJTs, or bipolar junction transistors. But there are also field effect transistors. You heard them called FETs. MOSFETs are a particular type of FET that is made from a metal oxide semiconductor. And then JFETs are junction types. And then there's IGBTs, or insulated gate bipolar transistors. And so they will have different schematic diagrams depending on the type of transistor they are. You won't see these on the test, but it's interesting to observe these. I'm not even sure why you would use one type of transistor over another type. It depends on other things going on in your circuit.
What kind of bit is this? This one is
Gate feds, MOSFETs, but the reason why they use them, a field effect transistor more closely resembles a vacuum tube than the transistor does.
Okay, good to know.
Matter of fact, at the telephone company when I worked 2 years ago, we were pulling out the vacuum tubes and replacing them with what they call FETrons, and direct replacement. without
So
heater.
Stan says that the FET type two or FET type transistors work more similarly to how vacuum tubes did. And when he worked for the phone company, one of his jobs at one point was to replace tubes with, what did you call them?
FETrons.
FETrons, which was basically a FET transistor in a package that made it plug into the same socket that the tube did. But it didn't have to have the filament that heated up because it didn't need that, being electronic. And
Yeah. For so many months and recalibrating with FETrons.
well, plus they can burn out too. So, the filament can go bad and burn out. If we have time, I'll tell you a story about a tube-based computer that I was able to tour one time. Um, so let's move on to logic circuits. So we're going to talk about a little bit, how much time do we have? We're good on time. Okay. So logic circuits, we've talked about these components, a lot of different components, and we use those to build circuits. Now, when you start getting into the digital stuff, you start wanting to think about things in terms of logic levels. And even though there's actually a specific voltage in that circuit, you don't really think of the amount of voltage going through there. You think of it either as being on or off, okay? Or the signal is present or it's not present. Now, if you watch it on a scope, you'll see that any one of these components will have a rise time where as you apply the current to it, it will slowly build up. And I say slowly, I mean, it happens in a matter of milliseconds, but it will slowly go up to the level. And then when you take it away, it will slowly go back down, right? Or decay back down to zero. So as we think about things in a logical fashion, the key factors are, we don't care about those guys. The key factors are the presence or absence of that signal, or you think about it as being on or off, or in binary language, either 0 or 1. Okay. And so ultimately, under the covers, all of this voltage is moving through resistors and transistors and things. No, that's all happening in there. But you can encapsulate that and think about it at a higher level. And that's where we start talking about these logic circuits. there are certain symbols that you will encounter when you're talking about these logic circuits, and we call these things gates, okay? And so I have several different diagrammatic representations of gates here. We're going to talk a little bit about how these things are made and then what we can do with them. Okay, so there's some different types of gates. There's and, NAND, or, NOR. There's the buffer, the NOT, or inverter, the exclusive or XOR, and the exclusive NOR, or XNOR. And we'll just to run through how these work really quick. If I've got an AND gate, it has two inputs and one output. If and only if the two inputs are both on. No, sorry.
Yeah.
Yeah, so it's so if we call this A and B both have to be on for the output to have a signal. Okay? In an OR gate, if either one of these is on, then there will be an output. Okay? In a NOT gate, if there is a signal coming in, there won't be one going out. Or if there's a one on this end, it'll be a zero on the other end, and vice versa. If there's no signal coming in, it'll generate one going out. So if we look at the NAND gate, it basically takes an AND gate and puts a NOT on the end of it. So whereas the AND says both of these have to be on for an output to come out, in the NAND, both of them have to be off for a signal to come out. No, either one can be off. Either one can be off for a signal to come out, right? For a NAND. Because
both have to be off.
do both have to be off?
What does an OR do?
Well, okay, think about it this way. If we take an AND, right? If one of them is on and one is off, then this is off. And so that, in that case, this would be on. Because we are inverting the output. So if, only if these are both off, would this be on.
No, one goes off.
If one of them's off and one of them's on, then
You've got one on.
the signal would be on coming out of a NAND, right? And I hate this stuff.
So for AND, both of them have to be one to get a one out.
Yes,
For NAND, both of them
have to be zero
Both of them have to be one to get a zero.
to get a zero out. So if either one is on in an NAND gate,
There we go. That's it.
or both of them are on, then we get no signal out.
Both of them have to be on. The rest of them.
Okay. Let's visualize this again. All right. Now I'm with you. I'm getting you, but it's, you got to bend your mind around this, right? It's like confusing because you don't usually think about things in this way. There's actually a symbolic representation of these that I'm not going to go into, but it actually allows you to think of it mathematically, which I probably should have put some of that in here, but I did not. Okay, so if one of them is on and one is off, then the output of the AND is going to be off and the output of the NAND is going to be on, right? If they're both on, then the output is still going to be off at that point. If either one is on or if neither one are on, then the output is on. Only if they're both on will the output not be on. Yeah, kind of. I mean, it's been a while.
If you had written it down, it would have been AB, and then AB for a NOT gate would add a bar across.
Right,
And that's the Boolean algebra.
right. Yeah, which I did not write down in this presentation, which I probably should have. Okay, so the OR gate is the same kind of thing, right? If either one or both are on, then the signal is on. Now, the XOR is a little different. If either one is on, then the output is on. But if they're either both on or both off, then the output is off. Right? Right. And then the XNOR is the opposite of that. It would be if either of them are, if both of them are on or both of them are off, the output would be on. If only one is on, then the output is off on the XNOR. Oh man, this is so fun. Um, and then the buffer just delays the signal going through, right? Or maintains it. Yeah, it just maintains that signal. Okay. Okay, so
Maybe when they taught this kind of stuff, they use speech diagrams.
I'm not familiar with that. Is that like a grid?
Simplify the circuit. So if you have like four inputs coming into one, like A, B, C, and D. And so if it was A, B naught, C, D naught, then you could put on the speech diagram and you could pull it back off in a simpler form.
That would be interesting to see how you do that. I would like to see
Love
that.
doing those. And
All right.
Incidentally, real quick, the way we do this nowadays, it was the C code, the language.
Yeah,
Same syntax. as C.
yeah. Um, yeah, what is it? .i files.
It's Verilog.
Verilog.
Verilog's funny,
Yeah.
but the syntax for this kind of building is the same. Just use it.
Yeah. All right. So how do we build one of these gates from components? Because ultimately, all these things are built from these components, right? These components that we were talking about beforehand. So for an AND gate, there's a couple of different ways you could make it. I just picked one. And in this one, there are two transistors, and you can see they're both NPN types, right? They're both pointing out. And I have two inputs. Don't worry about the resistors. They're there to make the actual circuitry work correctly, right? They draw the power through. Yeah.
It's not a bias, it's just with a bipolar transistor, you got like a short circuit there, so you can't just.
Yeah, I think about it as something to cause the power to flow through without burning everything up, right? To slow down the current going through there, essentially, or reduce the amount of it. Okay, so I've got a signal here at 5 volts. That's just like a base signal. And then I've got two inputs, and those are attached to the base connectors on these two transistors. So remember we talked about if this signal is present, then the transistor allows this current to go through. So in this AND gate, if either one of these is not present, the current is going to stop there. It's not going to go through the transistor. Okay. If both of them are on, then both transistors will allow the current through, and I'll be able to take the signal off here. Don't worry about this part either. This is just to give it somewhere to go, right? Yeah, so I can measure that voltage as being present here. And that's essentially how an AND gate works. If both of these are on, then this is on. If both of these are on, then this light is going to come on, right? If one of these is not on, the light won't come on. If neither one is on, the light won't come on. So that's basically how an AND gate works. These are the basic gate types that we typically work with. The AND, the OR, and the NOT. And again, we can combine those into other things, right? So we'll talk about that in a second, how we actually turn these three things into more. But in this one, if the output is on, if and only if both inputs are on the OR, if either input is on, then the output is on. And based on that description, can you think of a way to change this circuit so that it would work that way? You could use a couple of diodes, but how would you do it with transistors? Basically what you're going to do is feed the output from one transistor into the base of the other one. So you're either allowing current to flow through that one or not, depending on if that signal is present or the other signal is present. But you can visualize how you would change that circuit to make an OR gate. And then the same thing with an inverter or a NOT gate. You can see how you would use that, how you would build that with a transistor and say it's going to do that, right? Yeah. So other gates can be made from putting these gate types together. Now, we don't normally do this because we would just build the gate directly out of the transistors, but you could take those basic types. If you wanted to produce an exclusive OR, all you need is a couple of AND gates and a couple of inverters, not gates, and another OR gate at the end here to combine the two signals. And that gives you an exclusive OR. So if A is on and B is off, right? Well, let's start with A and B both being off. If A is off, then the output of this AND gate is going to be off.
Oh, email
Right?
the test.
And so in that case, this output is going to be off. If B is off, then if we follow this one, this AND gate is not going to allow anything through, so it's going to be off. So we'll have two offs going into our OR gate, which will result in an off coming out, right? So if both of these are off, then this doesn't produce anything. Now let's say if just A was on and B was off. So this AND gate gets an on from this side, and then from the B side, remember it's off, we invert it to being on, and so now this gate is getting an on, right? So it's going to pass an on out through here, and this OR is going to pass it on out. Now, if we switch it the other way around, in this case, this gate is going to get an on from the B, and from the A side, it's going to get an inverted off. And so this is going to get two ons, and it's going to produce an on. Now, what if both of these are on? In that case, what we've got going on here, this is getting an on from A, and from B, it's getting an off. So it's going to produce off, right? Same thing happens over here. This is getting an on from B and an off from A, so it's going to produce off. And when we OR the two offs together, we get an off out the other side. So this is how an exclusive OR can be built out of our three basic gate types.
Yeah, they use them as a competitor.
Yeah. Again, we wouldn't normally build it out of these gates. We would take the actual components and build it directly, and could combine components and use fewer components in order to do that. But logically, we can think of it as a combination of this. Okay, we're getting close to the end here. So this is where we start getting some kind of cooler stuff. This is the Intel 8086 processor. And the way this picture was made was a guy took an 8086 and he carved off the plastic so that he could get to the actual chip. And then he took pictures of it and produced this. And what you can see happening in here, this chip, which is about what, 2, maybe 3 millimeters on a side, has 29,000 transistors on there. And this is what we call an integrated circuit. We print these components onto the silicon layer using a metal oxide, and we're able to make tiny little transistors and little wires to connect them and all of that. It's really pretty cool. I have a link at the end to an image of this that you can actually blow up and zoom in on and see all of the detail of the 8086 processor, which is pretty cool. But you can see there's several different components laid out on here. There's some control circuitry up here. There's a decoder here. There's an adder up here. These are the upper registers and the lower registers. And then the arithmetic logic unit down here. And this also includes an adder. This adder is only used for address adding. It combines these two parts together to make an address that is a 32-bit address instead of a 16-bit address. And then this section over here is the microcode. And what this is basically a list of instructions for the ALU. The ALU can only do 3 things. It can add, it can subtract, and it can shift bits. but the microcode tells it if you do those things in this order to the information, then you're multiplying. And so it implements the multiply two numbers opcode as a sequence of steps for the ALU to perform. And all the other opcodes that are used in the 8086 programming language, assembly code, are defined in this microcode that tell the ALU how to do its thing. It's really amazing when you think about how this stuff was designed and built. This chip was developed in 1978 is when it was released. It's probably under development for at least a couple of years before that. I interviewed with Intel in the early 90s, and at that time they were working on the Pentium. The Pentium was, yeah, they were working on the Pentium, and then they had the group that I would have worked for. They had two separate projects, so essentially two separate groups. One group was working on the Pentium, and the other group was working on the 686. And they were doing it all on IBM RS-6000 workstations. And I didn't end up taking the job because it didn't end up being a very good offer, and I would have had to move to Portland. But it was interesting to learn about what they were doing and how they were doing it. Dan.
My best friend, he worked for Intel. And his job is to sit in front of a big screen in a simulated electron microscope, and he designs the spacing between the traces. We're talking nanometers.
So that the electrons don't accidentally get from one to the other. Yeah. So this one was yeah, Stan, go ahead.
Used to work for Texas Instruments.
Yeah. Yeah.
We had people that buy other companies' integrated circuits, gave them telephone.
Take pictures. Yep. Yep. That's why you could buy 8086s from several different manufacturers, and they were all compatible and did the same thing. So
Assembling these, they used a gold wire, solid gold, 1/10 the diameter of the human hair. This little torch, and they heat up the end of it, it would form a little molten ball, and you touch it and would weld it to that. That's what you call the ball bond process.
yeah,
You put on transistors as well.
when you look at the expanded version of this, you'll actually see those little wire traces coming in to the pads that are around the outside of this chip that bring in and out the circuits. And one of the interesting things that I observed was that two of the pads actually have two wires going to them. One is the power and one is the ground. And they needed two wires because one wouldn't carry enough current. So they ran two wires to each of those. And those little wires end up going back to the pins on the outside of the package. So,
And that is where an EMP fries.
yes,
CPUs.
yes, because an EMP comes in there and just kind of blasts this thing. And any of these little traces look like little antennas, and they pick that EMP up and they overheat and they melt. And there goes your CPU. It just becomes garbage. Anyway, so this is the x86 or the 8086 that pretty much all of our desktop computing up until the last, what, 5, 10 years ago was based on these types of CPUs, right? Except, well, Apple has gone to their own Apple Silicon, the M series.
Has a different layout. The Intel has nearly over 10 times as many instructions.
So I actually have a picture of the Intel Core i9 processor blown up in the same fashion. This processor has, gosh, it's like, I think I said it on the previous slide. 25 billion, I think it was. Yeah, 25 billion transistors. Again, on a package that's, maybe at the most a centimeter on each side. Yeah, that's true. That's true. If you look at what's going on in here, you see like all of these, what they call Raptor cores. Each one of these is a processor like this guy. There's 8 of them on here, plus there's these guys that are processors, there's these guys that are processors, there's the memory controller over here, there's the display control logic over here. There's a lot of stuff going on this chip, and it's just going to get more and more complicated as we develop technologies to allow things to get smaller and smaller. They're working now on quantum computing, which has more than one state. It's not just on or off. It's like on, off, and maybe on and maybe off, right? So it's, yeah, there's like,
It isolates that part of the process of the rest.
yeah, there's some really cool technologies going on in hardware development nowadays that if you have a chance to look into it, it's really quite interesting.
So, just so you know, my friend, we've been at this point for a while, we've gone so small, they've stopped making the transistors any smaller because, at the atomic level, things are.
Electrons are too big.
Yeah.
Yeah.
And so they start to reorient things. They start put, like we see this in memory, they start putting the memory up instead of down, right? So they use some crazy stuff. And then you have the quantum. That's the next logical step.
Yeah.
Is quantum processing.
Yeah.
Because we've hit
The limits.
physical limits
Yeah.
of this.
Yeah. It's an amazing time to be alive, that's for sure. So I've got some links on here. There's Geeks for Geeks. They have a great discussion of logic gates, how they work and how you can make them and how that can, how they all function together. There's this learning about electronics. They've got a ton of circuits that you can build that do different things. This one, a look at the die of the 8086, that's where you can find that huge blown up picture of the 8086 processor, and you can actually like zoom in to where you can see the different traces within the chip. Pretty cool. And then this video on YouTube, I don't want to include it in the presentation because then YouTube will get mad at me when I try to publish our presentation. But this guy builds a adder out of water, little tubing and little containers that he uses to make an adder. And he's talking with another guy who's done the same thing with dominoes. Can you imagine building a computer out of dominoes?
It's like a digital adder.
Yeah, a digital adder. Yeah. Yeah. So watch the video if you get a chance to. It's pretty fun.
However, when the controller light comes on, it says reset.
Well, the way he resets his thing is he picks it up and tips it upside down so all the water pours out. And then he sets it back. Now he's ready to start again. It's a 4-bit adder. So he's got 4 bits of input from 2 different sources and 5 bits of output that he can produce. So he handles the overflow by just having an extra bit. And so he can add numbers together, numbers up to 15 he can add together and produce a result which you can read based on how much water is in each little container. It's pretty cool. It's pretty cool. That's my presentation, and I did promise that I would talk a little bit about the computer that I walked through. I have 15 minutes. So back in the 1970s, I was in Civil Air Patrol as a cadet member, a teenager, and we had the opportunity to have a tour of the Sage Blockhouse at Malmstrom Air Force Base. The Sage system was a computer system that was designed and built in the 50s to track all things that were flying anywhere in the northern hemisphere of the Earth. It received inputs from the DEW line, the Defense Early Warning Radar line across northern Canada. It received inputs from the east and west radar inputs that would watch over the oceans. And it would feed all of that information together into this network. And there were 7 blockhouses across the US. One was in Montana at Malmstrom Air Force Base. There were several others at different bases. And each one of these buildings, this building was, the walls were 6 foot thick, pre-stressed concrete. You had to basically go through a combination lock door to get into the place. Inside, the building was probably 5 stories tall outside. Inside, it was 3 stories. And the first floor was the computers. There were 2 computers, and each one took up about half of the floor space inside this building. And they were all using tubes. So there were racks and racks and racks of tubes, basically in this large room that you could walk through. And they used drum memory, which, if you think about a large rotating 55-gallon drum full of oil, and magnetically you write on that as it's going around. It's going around at probably, I don't know, 300 RPM or something like that. And so you know where you're putting things on there, and you know how long it takes for them to come back. So the way you implement delay loops is by saying, I want to read a particular memory location off of this drum, and then I want to read the next previous one. And you know how many milliseconds it takes for the drum to go around. And that's how you implement a delay loop on this computer. But this computer would pull in all of this data and crunch it and turn it into a representation that could be visualized on these scopes. And so the second floor was just offices. There was nothing big there. The third floor had this control center, which had dozens of these terminals, and they each had a big scope about like this big around. And on there, you could see the northern US and Canada. And it had like the lines indicating where the breaks between the states and the provinces were. And you could zoom in, you could zoom out, you could pan around from one part of the country to the other. And on that screen, you would see these little moving dots. And each moving dot was an aircraft that was flying and that was being picked up by this radar. And they would all have some information written on the screen next to each one. And the operator had a light gun, which was like a little thing, like a pistol. You could point at one of those dots and push the button, and then an auxiliary display would light up with information about that particular aircraft. It would tell you how high it was, how fast it was going, what direction it was going. If it was on a filed flight plan, it would tell you the radio frequency to use to contact the aircraft. All of this information right there. Any of the operators in the room could see this. One of the things that I remember being amused by is we're looking over the guy's shoulder as he's showing us how this display works. He zoomed in around Malmstrom Air Force Base, and you could see on the one side little dots moving like in a line. And he said, you see these dots over here? They don't have any information on them. These are cars moving on the highway outside the base. And you could actually see them on the radar. And he could pick one and it'd say, it's at 0 altitude and it's going 60 miles an hour or whatever. And so he could pull that information up. But the concept was, if missiles were coming at us over the pole or something, or from the oceans, this system would see them, identify them as not being recognized. And if they were like airplanes moving, we would scramble fighters to go look at them. And the Russians would do this. They would send their bombers over and fly around near our airspace. And we would send F-106s or at the time it was F-106s. Nowadays it's like F-16s or something. We would fly them up to go check them out and basically tell them, move along. And then they would veer off, and they would do the same thing with our guys, right? We would probe their defenses all the time, and they would do the same thing. If you think about that, if you saw something coming, like a wave of dots that you didn't know what they were, and they were moving at a certain speed, you would think those are inbound missiles, and you would get 30 minutes of warning.
Were there people watching for it, or did the computer?
The computer would detect things that didn't have information about them. And it would present that information to the operator. The human was in the loop. They had to say, oh, I see that it's just one thing. It's probably nothing. It's, it's probably a twin otter that didn't file a flight plan and it's going, 120 miles an hour or something in northern Canada. They do that all the time. But if it was at a higher altitude or if it was moving at a certain speed or something, that would be an indicator that they needed to scramble a fighter to go look at it. And somebody would fly out there and look at it. The F-106 could actually be flown completely automatically by that system, that computer system. So the system would generate the flight information and upload it to the aircraft. And the pilot would basically take off, turn on the autopilot, and it would fly it to wherever the intercept point was. And then he could look at it visually and decide what he wanted to do at that point.
Pretty high tech for all tube based.
1970s, although originally 50s technology running these things. The same capability that was in that blockhouse was in the AWACS aircraft that fit in a single rack of equipment. And nowadays, that level of computing is probably half of what I have in my phone, right? But
How, if that would be like 100.
well, I don't know. But it was state of the art at the time, and it was pretty cool. The blockhouse was designed to run on generator power all the time. They had 7 big diesel generators that ran the thing, and it only took 2 to provide enough power to run the entire building. There would always be 4 running, 2 active, 2 in hot standby. So if one failed, it would automatically bring one of those other ones online. And then 2 were in cold standby. So if one of the actives or one of the standbys failed, it would spin up one more of the cold standbys. And then one was always torn down for maintenance. So they would do rebuilds on them and they would cycle through them. So.
And at the end of every day, you would hear the computer say, wouldn't you rather play a game of tic-tac?
How about a nice game of chess? No.
Are we gonna do any more on the electricity, next week?
Dan has some more stuff next month.
Jan, and then Jan's gonna put it down, and then it's gonna be the rest of the club.
I'm actually gonna bring in an ENIAC computer, okay?
You're gonna bring in an ENIAC?
Yeah. Yeah, I need them to wipe those doors.
Yeah. But yeah, I mean, not many people have walked through a computer before and it was pretty cool to do that.
Reason why I ask you. I have, some material and I have some demonstrations, for example, the computers you were talking about, the gates and so forth. I have trainers that do all that, have all the gates and everything.
This is what I'd like to do the first Thursday of next month.
That's March.
Yeah.
All right, I'm going to wrap up the recording because I think we're about done here. So let me close this down. Thanks, everybody. Appreciate you all for attending. And this recording will be on the website at some point. I'm not sure exactly when, but as soon as I can get it up there. All right. See ya.